Hello? Yep. Okay. Hi guys, so first up, just to apologize to all of Prem, Will and Joe, because this is basically the NetDev talk again, so you three are allowed to go onto Facebook and do whatever you like for the next half an hour, 45 minutes. So guys, we're gonna take a little bit of a different turn now. We're gonna be looking at a slightly different aspect of how you can do data plane acceleration. So everything we've spoken about so far, whether it be using in the SDK, whether it be using P4, it all revolves around you guys writing custom code for a device, whether that be a NFP, whether that be the Barefoot Tofino chip, whatever that device is, you're writing code specifically for that device. What this is going to be about is we're going to talk here about how you would do transparent offload. So you write code which is designed to accelerate your kernel, and then that would be transparently offloaded to the NIC and transparently accelerated. This means no extra code, no extra work to use the NIC. Simply, you have the NIC with the correct firmware on, and it runs. So what I'm going to do is, hopefully, at the end, I'll be able to show you a live demo. The slight issue is that this is running on servers in the UK, and I'm having some fun with my tunnels at the moment. So if that doesn't run, I do have a video as a backup plan. So we'll be able to show you at the end actually how this would work. But first up, just to run through exactly what we're going to be doing, what eBPF is, what our motivation was for using this, and then also some slightly more technical details in terms of how we actually implement this. This is all upstream in the Linux kernel. So if you have 4.9 on your server, this will just run. Okay. So first question up is just for those in the conversation who don't understand this yet. What is eBPF? eBPF is and I've stolen this from PlumGrid, so if there's anybody from PlumGrid in the audience, credit to you. It's a universal in-kernel virtual machine. It's got 10 64-bit registers, 5 12-byte stack, infinite as long as obviously your hardware can take it, size maps, and a well-defined bytecode. And this is used with a stable sort of in-kernel JIT compiler. Now this is on x86, I believe it's now on ARM64 and also on PowerPC and various other platforms. The LLVM backend means there's a pretty well optimized compiler there to support the producing of your bytecode. Sorry, there's a bit of a typo there, from C. Tools also exist for Go, P4 and various other coding languages. And eBPF, just to be clear, it's a subset of C, so it allows backwards jumps, but you're not allowed any infinite loops. So that's where the verifier in the kernel, which I'll speak about later, comes and gets involved. Make sure that your programs fit within the constraints of an eBPF program. So which is 4K of bytecode instructions plus no infinite loops. So you have to have a guarantee way out of the program because you don't want people to be able to completely kill their kernels. Also, there's a bunch of in-kernel helper functions that add any additional functionality that you can't do with standard eBPF. These are things like working with C groups. There's potentially going to be some stuff to do with security, with encryption, and there's various other helper functions there already. Things like looking up entries and maps and so on. So just to explain where this fits within the networking stack, so you have. This is sort of a rough overview of the networking stack. This is very, very, very high level. So I apologize to anybody who thinks anything on here isn't quite correct. Basically, the hooks we're focusing on are the ones in XDP and TC. So that's where you would fit this into the kernel, and this is where we would offload it. Now, there are other eBPF hooks up near the top of the networking stack. But those aren't what we're focusing on. Those are more for tracing and those types of things. So what we're focusing on in terms of offload for performance are TC and XDP, which is a new driver space hook, which is now in the Linux kernel. So then, okay, why are we doing this? Why do this type of offload? Why not just write your custom programs? Why not just write your own stuff? And why not just use various custom solutions? So the problem that hit me here was what I call whack-a-mole. So if you start writing your custom programs for custom devices all the time, and you're us, then you end up in a position, for example, when I was at NetDev recently, there were talks on how to do TLS offload, how to do IPVS offload, And these are all things that are being implemented by hyperscale data centers in the kernel using eBPF. So why are we trying to whack-a-mole, there's this program which people are using, oh, we can offload this, oh, we can offload that. No, instead what we do is we provide people with a coherent, transparent framework whereby the implementations that they're using within the Linux kernel, they can offload totally transparently. That's the idea here. This avoids vendor-specific solutions. It means we're flexible. It means we're portable. And, yep.
Another important thing that I guess Johan mentioned is that by making it transparent and consistent with the kernel and the software implementation, that really enables you to not. It's the only way you can easily solve this state migration problem.
Yep. No, exactly. So just to repeat that comment, there's this key issue about state migration. So as soon as you have intelligent NICs or you have intelligent devices within your system and you have loads of state migration going on, unless you're transparent with the kernel, that means you're going to have to add in a whole load of new infrastructure to be able to do that. So being in sync and being in state with the kernel allows you to avoid a lot of those issues. That's a very good point. So why eBPF? As I've already discussed, it's a well-defined framework. It's well-constrained. The implementation is actually fairly ideal for very multi-core architectures. You've got per-core maps. You've got a very well-defined way of actually looking at particular threads. So that makes it a lot easier to be able to port it to a many-core solution like the NFP. And also, it's the programming method used in XDP and probably the most flexible one used in TC. And that makes it a very good target for this type of general networking offload, which is what we're looking for here. In terms of target architecture, this is just the NFP-based SmartNIC. You guys have seen probably quite a lot about this today, but just to quickly repeat it, you've got a huge group of fully programmable flow processing cores. These are arranged into islands containing 12 of these flow processing cores each. There's combined with some islands which contain specific flow processing cores with hardware blocks to handle things like crypto and various other things, some form of processing. So if you're passing packets up to the host or if you're doing a couple of other things, there's an arm there to control the system as well. So there's a few other bits and pieces on there. But the key thing is the 72 to 120 flow processing cores, which give you stateful processing. So along with that, you've got per core, you've got, I think, 12 kilobyte of local memory on each one of these 72 cores. And then per island, you've got 64 kilobytes of local scratch and 256 kilobytes of target memory. Now, the target memory is where packets will sit. So if you see within this here, with our sort of system here, you have the packets coming through the ingress. They hit a programmable pre-classifier. This is what ensures that afterwards we can reorder the packets correctly, because obviously if you have 72 different cores with 500 odd threads running at once, there's a lot of reordering to do at the end. So this is a key component, is actually having the pre-classifiers there to be able to take the packets, tag them with some metadata, which means at the end we can put everything back into the same order. That's why we're able to get the performance we get, that's why we're able to get the throughput we get, and minimize latency as much as possible. Packets then head through to the CTM, and then from there they get processed within the flow processing cores and reordered and up to software. So obviously this is the RX path. Now, just to give clear the flow of an eBPF packet, so what we would usually have is you have the packets come in. We would have specific cores within the NIC that are running eBPF. So you have the standard NIC running, so you can have whether you have the OVS NIC running around the outside, whether you have most likely a sort of a more what we call a core NIC, which is a sort of a fairly intelligent standard NIC with particular microengines which are focusing on eBPF. So you would run through the sort of standard NIC data path, and then after going through a particular core NIC flow processing core, you would run to the actual eBPF flow processing core. So that's how that would work out. And then afterwards, again, through the reorder block and so on. This is the flow processing core in more detail. I'll try and spin through these because obviously we're slightly tight on time now. This just gives you more idea of how everything fits together. You've played with the chip already today. You've got some idea of how this all fits together. You've got 128 32-bit A registers, 128 32-bit B registers, and these interact with each other. So that's the key thing, is that you've got these A registers and B register banks, and they interact with each other. Usually,
Is this framework targeting only SmartNICs?
This is the SmartNIC. This is our architecture. So at this point in time, this is the architecture. On the next slide, I'll explain how eBPF then maps to this. So this.
To your previous comment about core NICs, what did you mean by that?
Oh, so by core. Okay. No. So what I meant by core NIC was core NIC is a brand name we kind of use internally for our standard NIC. So this is a NIC which is not, shall we say, it's not the OVS offload NIC. It's a standard NIC providing standard NIC offloads with a few other things around the outside. So that's how you would fit it in. So that's what I was saying. So you would have certain MEs with one set of firmware on, other MEs with a different set of firmware on. That's how that would fit together. So again, this is the chip. This is the flow processing core. You've got 8 threads. So usually you would divide your registers equally. So I've said 8 threads. If there's 8 threads, each one has 16 32-bit registers in A bank, B bank, transfer registers, next neighbor registers, and so on and so forth. You can change that around if you need to, but let's keep it simple and say that's the way it is usually. This obviously is actually quite good for mapping the eBPF machine into. You've got 4K of bytecode instructions. We have 8K of NFP assembler instructions. So we can map those in there. That can usually fit. We have the 10 64-bit registers. Now we can fit those into our A and B banks plus some of the next neighbor banks. Obviously you're saying, hang on, you've got 32-bit registers on the one hand, you've got 64-bit registers on the other hand. That's going to cause some reduction optimization. I'll talk a little bit more about that later. There's some things we can do to significantly increase performance there. This is the programming model. I didn't quite finish on here. So the 512 byte stack would usually go into your local island memory, and then maps can fit into DRAM and SRAM. The programming model, so this is again coming back to where I was, about this being a transparent offload from the kernel. So if you have the system running, you would have your BPF program, .c, push it through LLVM. You then have the actual object file, which you would then push through the verifier. The verifier ensures that you're not breaking any of the eBPF parameters. This means that you have not got any infinite loops, you're under the 4K limit, and there's also actually a branch limit within the verifier. So the verifier ensures that with all the branches, you actually, I believe it's under 64K from memory, instructions are actually hit. So this ensures that you can't make something that's almost an infinite loop to try and basically use that as some form of attack. And then finally, anything else in here? So actually what we then do is we have our JIT at the same level as you have the kernel JIT. And this then leads to us being able to convert the eBPF bytecode, which I'll show you in a little bit, into NFP assembler, rather than it being converted into x86 assembler. So that's a fairly key point. We're basically at that extremely low level is where we're actually making the transition. So everything you see as the user, everything you would do for the kernel, you change nothing. There's no reconfiguration, no anything. I will hopefully be able to show you this live in a little bit if my tunnels hold up, otherwise I'll show you a video. And finally, the last point here is that this translation reuses a significant amount of verifier infrastructure. So we've done some work in the kernel community to add a new header file, which means we can reuse a lot of the infrastructure. Yep.
So, as a user, when I write my program, for example, I guess UPF program, I need not be aware of micro engines, register operations.
Nope, nothing. Yeah. Now, all you have to be aware of is you've just used the ETH tool. There's an ETH tool flag, which you can set to whether the offload is on or off. You just set your ETH tool flag. And then if it can, it will offload the program. And if it can't, then it will leave it to run in the fallback path and software. It's as simple as that. Yep.
So you're saying that the intent is to write a piece of code that's going to run on the kernel by default, and that might be selectively offloaded to the SmartNIC?
No, the way that eBPF is used currently is that it's mainly used by a couple of sort of hyperscalers, and VMware Will, sitting next to you, is actually doing a lot of work moving OVS so they can be based on eBPF. What you will do is you write your eBPF programs to run within the kernel. So you write kernel code. This is to run in the kernel. And it's not that it's selectively offloaded or anything like that. If you run it, it will be offloaded if it can be offloaded. So obviously, if you write something, I can't think of any examples right now, but let's say there was something which in the future which came into eBPF which we couldn't offload, we would then not offload that program. And let's say there are some very simple eBPF programs which you could offload with a much more dumb NIC, then those would potentially be able to offload some of those programs as well. Yep.
So whether or not you, I guess how do you, so you're saying if it can be offloaded, it will be offloaded. But presumably there are instances where it wouldn't improve your performance to offload. For example, if you were making use of lots of these kernel functions frequently, or if your program was only executed once or something.
So you're saying if you use the helper functions a lot,
Yeah, if you
that,
use the helper
yep.
functions a lot, would you, are you considering, do you think that might be an issue, or would you consider,
What is what I think there is a user space API to choose as well.
Yep.
So if you are looking at specific cases.
Yeah, so there is, you'll see this later, I'm going to run the same program in software first and then in hardware. So we're kind of giving that responsibility to the user. If you're the user and you say, actually, hang on, this performance for this could suck because of reason X, then you just set the skip hardware flag, which I will be doing later. So hope I'll be able to show you that running. Yeah. Anyway, so this is just a quick couple of slides on sort of the basics in terms of how the offload works. So as you can see, this is what the kernel looked like before, I think, 4.7. Sorry?
What is your before referring to?
Before the offloads were upstreamed into the Linux kernel, hence before 4.7, I think it was. So this is before any of the offload was upstreamed into the kernel. So you had XDP, where you could run eBPF programs. You had TC, where you could run eBPF programs. You had the verifier, and you had the JIT. So this is what it looked like before. So I believe this first got pushed into the kernel, eBPF got pushed into the kernel like 3.15. XDP came a bit later. So this is no offload. You've got XDP, where basically the first use case for XDP was actually DDoS or DOS. So you can see that packets could potentially be dropped there or redirected back out. However, then if you go through to TC, you get the SKB and so on added on to the packet, whereas XDP is actually run in the driver space before you have the SKB added to the packet. And what we have now, so this is, I think, 4.9, which is where we've got everything in. You have the offload object, which is the hook from CLS-BPF. This also applies now to XDP. You have our hardware JIT translator, which is in driver space. And you have the verifier, which has had some modifications to it so that we can reuse a lot of the infrastructure within the hardware JIT. So this is all upstream today. This is in the Linux kernel. If you've got the latest Linux kernel, this is all there. And what we have also is a fallback path. So if let's say you have certain packets which can't be handled by the NIC, and you haven't said skip software, instead you're running on both, you can actually fall back. So we have packet descriptors for XDP, which would set the flag whether the packet's actually been acted upon or not. And for TC, there's a TC verd field, which is one of those fields hiding in TC, which you can actually use to set this, so that certain packets will fall back if that's not set. Again, translation. So first thing that happens is we check the hardware capabilities, and from there, we rerun the verifier. So first up, the hardware JIT will check what can we do. Then we rerun the verifier to check that the program will actually work with our implementation. We then collect the state, analyze it, and then the optimization, generation of using the JIT, and actually loading the image onto the NFP happens. So that's kind of the order in which this would happen when you get to the point of actually offloading it. And this is just a quick peek of the device path. I'm not gonna spend too much time on this stuff because I want to get through. This is kind of where we are in terms of roadmap. We've done most of the ALU instructions now, so we multiply and divide we've kind of left out because they don't get used a lot. Multiply, we have a fairly efficient implementation. Divide is a little bit more messy. Packet modification, that's now, or is it up yet? I don't think it's up yet, but we have our implementation internally. Basic maps, operation of the relevant fields within the packet metadata, I believe that's now done. And encapsulation. So that's kind of, these are kind of the next steps. This is very much a work in progress. We started work on this three months ago, maybe. So this is where we've got to now. Yeah, I think it was maybe July, maybe 4 months. This is where we've got to now, and this is stuff is being upstreamed into the kernel as we speak. So this is very much what we're working on right now. Now, one of the key problems you run into is how do you handle maps, which is exactly what we were talking about earlier, this transparent offload. How do you handle it when you've got maps in the kernel and in the device? So this was something we thought we were going to run into a lot of opposition about within the kernel community. It's actually turned out not to be the case, whereby we've now the most realistic way to do this is going to be first up, read-only maps are very easy because we can just pull them straight down. We have a copy in the host, we have a copy in the NIC, and there's no changes. That's pretty easy. We have read plus statistics. That's also not too tough because of the fact that we can just fire and forget. And then read and write, we've said, look, the most realistic way to do this right now is to make them device only and have some flags within the kernel, which tell different programs within the kernel whether they're allowed to touch these fields or not. And if they need to check anything on this, they would need to then sync it up with the NFP. So that would obviously be you'd have to be very careful in the way you handle that. We've spoken to the kernel community about this, and I believe we have some support, so we're going to be pushing this approach forward. Again, just finally a little bit of optimization work. So I mentioned earlier about the 32-bit state tracking. So this is things which we're now pushing into the verifier. So hopefully that will be up soon as well. This will lead to us being able to take, because a lot of these 64-bit ALU instructions that you end up with in eBPF, most of them are 32-bit ALU instructions. So instead of it taking us a bunch of instructions to process it in our 32-bit architecture, we can reduce those to a single instruction. That saves us a huge amount of cycles. There are actually other places, such as the example I've given here, where we're doing shifts at the same time as doing ALUs, that we can actually take 3 or 4 eBPF 64-bit bytecode instructions and take them down to one single NFP instruction. So all these kinds of optimizations are what we're currently working on within the JIT, and some of this stuff is also happening within the verifier. So there's a lot of work going on at the moment to be able to actually improve this. Then also there's things to do with clever caching and so on within the maps. Right, let's see if this demo works. Let's see if my tunnel's actually held up. If this works, I'm going to eat my hat. I don't have a hat, luckily. Let's see. Oh, it looks like it's still up. Okay, let's have a go and see what happens. So first up, we need to actually compile our program. So we've got a very small little C program, which I'll show you here. Yeah, I'm going to make this big. Otherwise, you might struggle a little bit. So, oh no, how do I do that?
Command-Shift+.
Yeah, let's see if that works. I'm not sure it's going to. Oh, yeah, you got it. Yay. Right. Can people just about see that, or should I try and make it a little bit bigger still? Okay. So what we have is we basically take the top of the SKB. So this is for TC. And we process through this. So we're going through L2, L3. It's a very simple little program, just going through those. And then all we're doing is we're checking TCP port. It's port 58. We're dropping packets. It's a very, very, very simple program. All we're trying to do here is show you how this is pretty transparent, pretty easy to do, and takes frankly, zero effort to pull down to the NFP. So let me go back to this one. I think we need some, there we go. Right. First thing to do is to actually compile it if it's, yep, it hasn't died yet. So what we're going to do here is just compile our program. So now we should have a object file. You just see, yep, this one here. TCP58 object, that one. So, oh, what's happened there? Anyway, so then what we need to do is, let me see if I've got these still in my history or whether I'm going to have to go back. Yep, so we had to do a reboot. So apologies, I'm just going to pull these out because if I try and type this stuff with the fact that this tunnel is going all the way over to the UK, it's going to be quite fun. So let's just do this quickly. So first thing we're going to do is just turn the offload on, as described. Oh, where's it gone? Yeah.
Or, oh, no, sorry, no, it's not slash. You're in the wrong directory.
Yeah, something's going on here. No, it's not going to be slash. Let me just go back. This is what happens when you try and do things live. I should have just said, yep, I missed out a slash. So let's just quickly go away. Now let's do that. There we go. So now what we've done is we've put the TC offload on. So you notice we just used ETH tool. So now the hardware offload is actually there. So we have determined that we actually have the hardware offload on. Next step. And we're just going to keep it small for now. So now we actually need to add the device to a Q disk. So this is all very simple. Yep, so I've actually already done that, so that's why it's saying it's already there. Apologies, I had my tunnel crash just before, so I had all the commands nicely set up, but now I've got to go back. So what we're going to do here first is that we're actually going to run this in software. So you'll see here, so the flags we were talking about earlier, we've got the skip hardware flag enabled here. So that means that this is actually going to be put in software for now. So for now, the hardware offload is going to do nothing. All that's going to happen is we're going to run this program in software. And so what we're going to do here, and we're going to have to make this one bigger as well. Okay. So now what we're running here is we've got a bunch of interface statistics. If it wants to let me have them. Yep. And so what we're going to be able to see here is just whether the packets are dropped. So we've got one thing missing here, actually. Let me go and try that one again. What is going on there? Ah, there we go. Okay, that's a formatting issue. So sorry, that one's going to have to stay a little bit small because for some reason the formatting doesn't want to let me scroll through. So as you can see, what we have here is we have hardware stats for the device. And then up here, we have actually the action stats for the TC. So what we're running in TC is on here. And then the hardware stats are on here. So all that we now have to do is just send some traffic across and see what happens. So first, we're going to send traffic which is legal. So this should not be dropped. And as we can see, works perfectly well. If we look at TC action, nothing's changed. We've still got 20 drop packets on here. Then if we send out traffic which should be dropped, then as you can see, transmitted because I sent through the wrong ones. Yeah, 0 packets received. And so you see, drops become 30. So this is all happened in software. Now what we're going to do is we're going to do this in actual hardware. So the counter to look at down here, I believe, is going to end up being app1 packets here. So look for this counter to increment as we do this, if this goes right. So what we're going to do now is we're going to delete what we had previously. So we're going to use this command here. And now we're going to re-enter the whole offload without the skip hardware. So this means that this is now going to actually run in the hardware. And now we run it. And again, no packets transmitted. And now the moment of truth. Yep, and we've gone to 80 there. So as you can see, this is actually, through a simple set of commands, we're able to take a program which is built for the kernel and actually use it in hardware. Now, this is all still very early, so in terms of performance numbers and so on, we haven't got that far yet. If we do some simple touch and pass test, or we do read, write, pass, we got to about 3 million packets per second. With 3 writes and 3 reads, we got to about 2.5 million packets per second. That is per core. So that's on each one of your wimpy little cores. So you've got 72 of those. Now, obviously, you're going to run into other bottlenecks. You're not going to get 3 times 72, but you're going to be able to get a fairly significant performance, and you're also going to be able to offload the host. Some use cases we've spoken about with this are things like IPVS, load balancing, and there's a few other use cases which we're working with customers on as well. But there's a lot of guys who are starting to use eBPF to offload certain things within their large hyperscale networks because it's significantly more efficient for CPU. And then once they actually want to optimize that a little bit more, if you put the NFPs in, you can just transparently offload the programs you already have there. And that's really what I'm trying to show here, and that's what I hope I've showed there. I apologize for it being a little bit sketchy there at the end. If my tunnel hadn't broke just before when I was sitting over there, it would have hopefully been a bit smoother. Thanks, guys. And any questions? Nope. Everyone happy?
So typically, how many ports can you handle in parallel?
So it depends on, do you mean physical ports? So with our NICs, we have up to the most ports you could potentially have running at once on the NIC. We have a configuration which would be 8 by 10. Yeah, I think that's the most we have. I don't think we have a, sorry? 8 ports of 10 gigs. Yep.
So I just want to say I think this is really great, and
Thanks.
And you know, opens up a lot of really interesting possibilities, and you know, it's really nice to be able to have the same program will run on different platforms, and
Yep.
if you plug in hardware, it just makes it better magically. That's
Yeah,
great, right?
no, that's the
Great for
idea.
users, it's great for you guys. I also want to suggest that, you know, it'd be really interesting. I mean, I know this is early, but you know, ultimately to see how close you can get with, you know, a C program compiled through BPF and then JIT it to the hardware versus, you know, native C compared on your development platform, which is probably your sort of hardware performance upper bound.
Yeah, no, that's actually something I've thought about a lot, and you know, it would be awesome if you wanted to compile something on the NFP and you just used LLVM. Yeah. That would be the dream in my world. If we can one day get there, that would be awesome. Yep.
How does this behave with the VMs? I mean, when you have this node in the host kernel, how does it give the services to the VMs?
How does it affect the VM? So
Basically, there is a way that some VMs can have offload, some VMs cannot have. Do you have any controls?
So you're saying, okay, I want to have certain BPF programs running for certain VMs down in the host before they actually get up to the VMs. That's what you're saying. So I guess you could do certain matches. So if there were certain match fields, then you can just match on those fields as long as they're within the SKBs. So layers 1 to 4, you'll be able to match on them and use those as the ways to do it. This has also been used. So one of the other use cases I'm seeing for this kind of thing, which is coming up a lot, is for use with containers, with C groups and so on, because it gives you an interface and you can actually use it. So there's some helper functions being added for C groups and so on at the moment, actually. So yes, there are ways to do that for specific VMs and avoid other VMs being affected. Anything else? Brilliant. Thank you, guys. Appreciate it. Thanks for listening, and sorry about the hiccups there.